Hello everyone, welcome to the lecture again. In the last 28 lectures, we have covered the static part which was half of the syllabus of this course. Therefore, it is right time now that we revise the concept that we have learned so far. So, this lecture is about the revision of the static part. And we started with the concept of the rigid body. A rigid body does not deform under the action of the forces. So, suppose I have this rigid body and let us say I have the ith particle and I have the jth particle, and let us say from the origin the position vector is Ri and Rj. In that case Rij, which is the spacing between the particles. So, this is Ri minus Rj mod, it has to be constant under the action of force. Okay. So, Cij and this is C is constant and this is true for all I and j. Okay. So, the body that does not deform under the action of forces is called the rigid body. Now, we also discuss what is sliding vector and what is free vector. Okay. So, sliding vector. So, let us say I have a body and on this body you apply a force. Okay. Then in that case the action of this force does not change if you apply the same force on the line of action of it. Okay. So, you can apply the force here or the same force you can apply here or the same force you can apply there. Okay. So, in that case the force becomes a sliding vector. So, a sliding vector has unique line of action, but not a unique point of application. Okay. So, for example, you cannot shift this force to some other location because then it will also introduce the torque. So, this is not possible, but along the line of action you can slide it. So, therefore, force is a sliding vector. Now, free vector. So, free vector is something that can be positioned anywhere in the space. Okay. So, for example, let us say I have this rigid body and there is a free vector. Okay. So, let us say this is a free vector. In that case this vector you can place anywhere in the rigid body. Okay. So, it can be placed anywhere in space. Okay. And the example is the couple. Okay. So, couple is a free vector. Now, we also saw how we can find out the resultant of the force. Okay. So, again let us say I have a rigid body and on this rigid body force F1 and F2 is acting, and let us say the angle between them is theta, then the resultant R will be square root F1 square plus F2 square plus 2 F1 F2 cos theta, and the resultant. So, this is the resultant R and the angle that it makes from F1, let us say it is alpha, then tan alpha will be F2 sin theta over F1 plus F2 cos theta. We also discuss the moment of a force. Okay. So, let us say I have a rigid body and on this rigid body a force F is acting. So, let us say this is the point about which I want to determine the moment. So, let us say this is O, then from O you draw any position vector r on the line of action of f. Okay. So, the moment about O becomes this vector r cross f, okay. And the magnitude of m about O is also f d, where this d is the perpendicular distance of this force from O. Okay. So, r is any position vector which run from point O to any arbitrary point on the line of action of f, okay. And d here is the perpendicular distance from O to the line of action of f, okay. Now, if the moment is produced by two equal opposite and non-collinear force, then it is called couple, okay. So, here the situation is following: you have this rigid body and let us say a force F is acting like that and another force F is acting like this. Then we saw that the moment of this force about any point O is equal to the force multiplied by the perpendicular distance between them, okay. And this moment about O is independent of point O. So, you can calculate the moment about, let us say, O prime or O double prime. So, in that case this will be equal to moment about O prime and moment about O double prime. So, therefore, this becomes a free vector. We also discussed that suppose there is a rigid body and on this rigid body a force F is acting at point P1 and you want to shift this force at some other point P2 keeping the same external effect. So, this can be done by having this force at point P2 and then you have to account for the moment, and the moment will be force into perpendicular distance d. So, this will be the d. Next we discuss the free body diagram and equilibrium analysis. So, for the free body diagram particularly we look at the support reactions, okay. Support reactions of smooth surface, support reaction from roller support, rocker support, pin support, and herein we discuss two cases: freely hinged pin and the pin that is not allowed to rotate. So, if the pin is not allowed to rotate, then it also support the torque, and the built in or fixed support. Okay. For the equilibrium analysis, we use summation f equal to 0 and the moment about a point should also be 0. Okay. So, summation f equal to 0, there are 3 equation, f x equal to 0, f y equal to 0 and f z equal to 0. Then we discuss the beam. Beam is a member which supports a transverse load. Okay. And if the load is distributed, okay. So, suppose there is a beam and on this beam we have a load that is some function of x. Okay. Then this distributed load, it can be replaced by the concentrated load and the total load R is equal to W dx, where W is the loading intensity and the centroid of the load, which is x bar measured from here, is equal to integral x W dx over R. We then discuss the flexible cable. And it has two cases. In the first case, we discuss the cable carrying uniformly distributed load along the horizontal. Okay. So, we have this cable let us say this point is A, this point is B, then we fix our axis at the minimum point of this cable. So, this is the x axis, this one is the y axis and let us say this height is h A, this height is h B, this length is S A, this length is S B and this length is L A and this length is L B, and W is the load per unit horizontal length. Then the equation of the cable y was y equal to W x square over 2 T naught, which is the equation of the parabola. Okay. Here this T naught was the horizontal component of T, okay, or horizontal component of the tension, and it was T naught equal to T cos theta, and that was constant. The tension in the cable can be find out using T equal to W square root x square plus LB square over 2 HB whole square, and for maximum T, so for T maximum my x has to be maxima, okay, and the maximum value of x herein is equal to LB. Now, the length of the cable can be find out using SB equal to LB 1 plus 2 by 3 HB over LB square minus 2 by 5 HB over LB to the power 4 plus dot dot dot. Similarly, you can find out SA, then the total length will be SA plus SB. Herein you have to note that your HB over LB has to be less than half. In the second case, the loading intensity was uniformly distributed along the length of the cable. So, this was the case wherein you can think of the cable which is hanging under its own weight. Okay. So, again let us say there is a cable and let us say this is the minimum point of the cable. So, we fix our axis here. Okay. This point is A, this point is B. So, therefore, this height is HA, let us say, this height is HB, this length is SA, this length is SB and this is LA and this one is LB. So, the equation of the cable in this case comes out to be y equal to T naught over mu cos hyperbolic mu x over T naught minus 1, and this is the equation of catenary. Okay. Here this mu was the weight per unit length of the cable, okay, and the tension T in the cable was T equal to T naught square plus mu square S square, or T can also be calculated using T equal to T naught cos hyperbolic mu x over T naught, or T equal to T naught plus mu times y. Now, the length of the cable okay, let us say SA or SB. So, S equal to T naught over mu sin hyperbolic mu x over T naught. So, you calculate this for SA and for SB and then you sum them up to find out the total length. We next discuss truss. Truss is a framework which is composed of members which are joined at their ends to form a rigid structure. Okay. And the basic element of a plain truss is the triangle. Okay. So, if you want to make a truss, you have to use 3 members which are joined together, and then you can extend this to make bigger truss. Now, if the members in the truss are M, the joints are J, and the support reaction is R, then if M plus R is equal to 2J, in that case the truss is statically determinate. That means we can find out all the forces that are acting on the truss, and if M plus r is larger than 2j, then the truss is indeterminate. Now, there are two methods to find out the forces in the truss. So, one is the method of joint, okay, and this method is more effective when you want to find out the force in all the members. Okay. When we want to calculate the force in all members of the truss. The second method was method of sections, and this method was more effective when we want to calculate the forces in only one or very few members of the truss. Let us say we have the following truss. So, this point is A, B, C, D, E and F, and at E there is a roller support, and let us say there are external forces also P1, P2 and P3. Then in method of section you divide this truss into two complete part, and we divide it such that it does not cut more than 3 members, because we have 3 independent equations. Okay. So, therefore, when we cut this, we have the following free body diagram of the truss on the left hand side. And then we use the equilibrium condition to find out the forces in the truss. Okay. We next studied the principle of virtual work. And the statement of the principle of virtual work is following: if a rigid body is in equilibrium, then the total virtual work of the external forces acting on the rigid body is 0 for any virtual displacement of the body. Okay. So, that means delta u should be equal to 0. Let us say the external forces P, Q and a moment m is acting on the rigid body. Then if delta x is the virtual displacement corresponding to force P, delta y is the virtual displacement corresponding to force Q, and delta theta is the virtual displacement corresponding to the moment m, then p dx plus q dy plus m d theta has to be equal to 0. Now, the next step is to represent this delta x, delta y and delta theta in terms of generalized coordinate. So, your x, y and theta, they should be represented in generalized coordinate. Okay. And what is generalized coordinate? Well, the generalized coordinate are the least possible coordinate which completely define the position of the system. Okay. For example, for a simple pendulum, the generalized coordinate is theta and the degree of freedom is 1. We then studied the stable and unstable equilibrium. Okay. So, let us say we have a particle on the following curve. Let me denote the minimum and maximum point on this curve. Okay. Then A and C represents the point of stable equilibrium and B and D, they denotes the point of unstable equilibrium. So, suppose you displace the particle from point A, then it has a tendency to come back, therefore, at point A the equilibrium is stable, while at B if you displace it slightly, it is not going to come back. Okay. So, therefore, it becomes an unstable equilibrium. And to find out the stable and unstable equilibrium, you find out the first derivative of V with respect to the generalized coordinate and put it equal to 0. And for stable equilibrium, your d2V over dq square should be positive, and for unstable equilibrium, d2V over dq square should be negative. Note that here q is the generalized coordinate. We next discuss the friction, particularly the static friction and kinetic friction. Let us say I have a rigid body on a rigid surface and the mass of the body is mg. In that case, the normal force N is going to act upward. Let us say you apply the external force P, then the frictional force is going to develop. And if you plot the frictional force as a function of external force P, then initially the F is going to increase, okay. It attains a maximum value. So, F max, which is equal to mu times N, and then the body start to move. So, in this case you have static friction and herein you have kinetic friction, okay. And this is the point wherein the motion just begins. So, this is the point of impending motion. The value of the static friction is mu s times N, and similarly the kinetic friction is equal to mu k times N. Okay. We also studied the force acting between ropes or belt and frictional surfaces. Okay. So, for example, suppose I have a peg and on this peg I have a rope. Okay. Let us say you have a weight W which is suspended like this and it is held by a force P. Okay. So, let us say this is T1 and this is T2, then we got T2 equal to T1 e to the power mu beta, where T2 is larger than T1 and beta is the angle in radian between the belt and the frictional surface. Okay. So, for example, you have this circular surface and you have a belt like this, then beta is the angle that the belt is making with the surface. Now, in this case if my T1 is larger than T2, so if T1 is larger than T2, then the same formula is applicable, but now we have T1 equal to T2 e to the power mu beta. So, finally, we discuss about the rolling resistance. And herein we assume that the deformation is there in the body as well as in the surface. So, suppose I have a body and this body is rolling. So, the surface and the body they deform. The deformation in the front, it retards the motion and the deformation in the back, it assists the motion. Okay. However, the retardation is always larger than the propulsion, and because of that the normal force N has a horizontal component, and because of that you have to apply a force to keep the wheel rolling at a constant velocity. Okay. So, the situation is following: you have this wheel and we have the normal force N which has a component along the horizontal, its weight is W and you have to apply a force F so that this wheel is keep rolling at constant velocity. So, to keep the wheel rolling at a constant velocity, we require a horizontal force F, and this force F is called the rolling resistance or the rolling friction. Okay. Now, let us say A is the point of application of this force N, and small a represents the horizontal distance between point A and the vertical line of center of the wheel. So, let us say this is A, then A is called the coefficient of rolling resistance, or A by R is also called the coefficient of rolling resistance, and the value of F comes out to be A over R into W or mu R into W, where mu R is the rolling resistance. With this, let me stop here. See you in the next class, wherein we will start the discussion about the dynamics part. Thank you.